accuracy. So out of that has shown the accuracy of around 70%. And so coming to the part six. So basically, the part six it's about the project report. It's like a short for like a making short of what we have done in all the important parts like part three, part four, and part five. And our aim of the project is to understand the data and build a convolutional neural network that works well on the CFA10 data by classification of images in 10 different classes. So, and also try to improve the model on the basis of the performance dealing with the data by reconstructing if necessary. So, about the data. So, the CFA10 dataset has 6,000 images. So, each class 6,000 images for each class, and that concludes 60,000 images that with 30 by 32, 32 by 32 pixel images in total. There are 10,000 test images and 5,000 training images, 50,000 training images. Pardon me. Each of these five training sub datasets and one test sub dataset in the dataset has 10,000 images. So exactly 1,000 randomly selected photos from each class make up this test sub dataset, and the remaining photos are distributed across the training subdata sets in random. However, some training subdata sets can have a disproportionate number of images from a particular class. The training dataset consists of exactly 5,000 photos from each class combined. So the classifications are wholly distinct of one another. So there is no crossover between the cars and trucks. So automobiles such as the cars, SUV, and similar vehicles are included, and only large trucks are referred to as trucks, and none of them contain pickup vehicles. Since our incoming data is sufficient to handle, there is no need to alter or reshape it. So the shape is now 32 by 32 and 3. So 30 by 32 represents the pixel size images, where 3 represents the channels, and none it could be any scalar value. And in this project, we performed building two CNN models classifying C14 data. So the reason behind building a second model is to enhance the scope of increasing in performance on the data. The model is built using traditional TensorFlow approach along with using GCP, the Google Cloud platform, which has been very helpful and very learning thing in this like in this course. Rather using the typical APIs like Keras, TensorFlow APIs like Keras, we have tried using the traditional TensorFlow approach. There is also a 1.5x version. This could help very helpful in applicable and useful and in the practical reality when you go and work for the companies. So these could be very useful for that. So I could draw some outcomes and conclusions from this project that will be covered next. So basically, let's talk about some explanation here. In the part three, I have built a CNN image classifier model to classify the Spartan image data that has 10 different classes. So you could see in the the part three, the first CNN model built has three convolution layers, and so there are three ReLU layers and the three pooling layers for it, and only the two fully linked layers, fully connected or connector layers that makes up the CNN model are complete. After building the three convolution layers and the pooling layers, we created the first FC layer that has been set the output size of 2048 and ReLU layer generated for it. So similarly, as I said before, we set up the steps like 5,000 here, and we test the network after every 100 steps of training, and we use the session. We used to run the session here, the TensorFlow session, to basically train and test the CNN model. So and also need to create an Adam optimizer. The Adam optimizer plays a key role in optimizing the model performance. And we also need to set the loading rate to the model of deep learning. So the outcome of building the first model, CNN1 has given some very decent performance. After Out of 5,000 steps, the model built developer demonstrated on the accuracy of 0.6113, that is 67% of training data. So in the part 4, we have the task to compare the test accuracy of two different CNN models that has to be built, and we test on two different datasets like C410 and MNIS datasets. Just give me a second, please. Sorry for my bad health, Excuse me for that. So we could draw some insights such as the CNN model performance on MNIST data is high, as that has a range starting from 0 to 98.77 accuracy, whereas the other CNN models, you know, other CNN models and built the other CNN model built on the C14 dataset has shown less accuracy range, starting from 0 to CT7.13. So you could clearly observe the gap between the accuracies of both models. You know, because some expected reasons have already been mentioned, like the better outcomes can be obtained by increasing the number of hidden CNN layers, such as convolution and FC layers, and in our model design, and the number of steps. And there is another reason that could have a greater impact. The number of steps or epoch needed during the training could also make the difference. If not done properly, it could result in the underfitting or overfitting. So in the part 5, we have tried to better or enhance the model performance by rebuilding the earlier into new model, so that the convolution layer has been removed and only two convolution layers have been preferred in the second model CNN2. So I would like to show a small glimpse of the difference in the code between the part 3 and part 5, that the slide chain that I have done here. Uh, you could see here. Whereas in the part three, so everything is same, like defining the functions here. So here comes we have defined the convolution layer one outputs, and the pooling layer for that, and convolution layer two outputs, and pooling layer for that, and ReLU layer and pooling layer for that. See, Eric, I have defined. I mean, I have created the third convolution layer here. So that was makes the difference, and this could lead to the different size of input and output channels, and that could give the size, size of the finally fully collector layer of around 2048. As you can see the shape here, and we also done the dropouts. Whereas let's come back to the part 5. So what is the difference here in the part 5 in compared to part 3 is, so here I defined the first convolution layer and second convolution layer, but I didn't define the third convolution layer here. So I just cut down the architecture. I just want to decrease the depth of the our design that has been built earlier, and to see how it works, how the model works on this, how model performs on this data, you know and as usual, this technique has worked for me on this data, that I'm very happy about that. I could see the 3% increase in the accuracy. That's a good improvement, rather than no improvement. The accuracy is a good improvement here. So let's coming back to our document. We are here like in the part 5. So we have set up the steps and all the stuff that I've been saying repetitively, and we have got the accuracy of around 70% on this part 5, like by altering the part 3 CNN model. And so to revise in the part 3, to conclude that a CNN model built with the three convolution layers and its pooling layers has has an achieve oh sorry uh, pooling layers has achieved an accuracy of 67.13% on the CIFAR data. And like in part 4, there are few conclusions drawn out by critically thinking about the comparison of the gap between the accuracy and data sets. So I just want to go back to the part 4 once again. Just let you know that the key points again, that I've been thought about this. So whereas I could clearly say that CNN works on the best on these MNIST data because there is a sufficient sustainability in the data, and the depth of the model also defines your model performance. Like the convolution layers, how many convolutions you're taking, and how many fully connected layers you have been taking for that, and how many steps are required for the training, and that also makes some difference, since if it's not optimal it could lead to issues like overfitting and underfitting. So since we built very simple CNN for this project, to be honest, I didn't like build like a 10 or 20 layers of hidden layers for this CNN model. I just made like a 3 or 2 layers to just see to make it simple for this project. But that what has done in this project. You know Let's come back to the final conclusion. Yeah, sorry. Before coming to the conclusion, I need to give the conclusion points for the part five. You know, I could see the good amount of rise in accuracy from 67 to 70%. So I have assured here the improvement of neural network performance. So simply I cut down or I will decrease the convolution layers in the model, and I have succeeded somewhat better in this thing. And coming to the conclusion of this project report, so finally we have done some good work in building CNN models, and also understand why the gaps between the accuracies differs, and a lot of insights also have been gained in understanding the data and depth in CNN models. So in the future, there is a lot of scope to work on building, huge models like with the usage of VGGNet, ResNet, DenseNet. These are the pretty good models, and analyze how they works on the different data. Just give me a second. I would like to address a few important points in the code since we have a lot of time left. So while don't so you need to be careful. There are a few things you need to be cautious about while loading the data here. You need to make sure you have to have all the batch files, and the batch metadata and the test batch data that is used for testing. So all these files that needs to be uh, downloaded rightly and uploaded well into the GCP, and again loading into the Jupyter. So basically, I'm showing the code in the collab. That doesn't mean I worked in the collab. I worked in the GCP VM based Jupyter, but I'm sure like I'm not showing you the Jupyter here because I didn't switch on the VM right now because it makes my network not easy, so that's why I just downloaded the files from there and just upload into Collab and just showing you that. So also uh, coming back to the train and test here, you could see here need to make sure while you need to feed the data, you write lively here. So a lot of people get errors. I also got error while I was doing that. You need to make sure you need to use the right extension here, like test images for the X and the Y to represent the test labels. So the whole problem 1.0 is used for the dropout, so anyway, I just coming back to the conclusion. Definitely in the future, I would like to try using the different models, uh, different CNN models, and try on the different data and see how the model behaves on different data, and how the depth of the architecture plays a key role, and how the epochs or steps plays a key role, in making differences of accuracies, and I need to learn more and more, explore about the CNN and the world of deep learning, and and thank you. It's been a very good time telling you about these things, and I hope you have a good video. You know, thank you. Have a good day.